Okay, so hello everyone. My talk will be much more theoretical. So it's about graphs, but also it's about game theory and probably economics. So it's about the area of fair division. Okay, so when does the question of fair division emerge? So there are a lot of situations in common life or in politics and so on. For instance, if someone divides inheritance, then maybe this inheritance consists of different objects like a parcel of land and some car and some other things, and there are several inheritance, and it could be a difficult task to split it fairly. Also, there are different situations, yes, in like divorce or some dissolution of a company and so on. And so it is very easy to split money because the money could be just split equally. But if the inheritance is not money but some complex objects, then it could be hard to split it equally. Okay, so the classical framework is called cake cutting. So this is an image from a Soviet cartoon. So these animals are sharing an orange. And so in this cartoon, the outcome was that the wolf got the peel of the orange, and all others got some scrambles. Okay, so on the question how to find a fair division. So formally, the cake is some private good with additive valuation, so it could be represented as a segment, a disk, or some other figure. And there are several agents, and each agent has a valuation of different parts of this good. So, and this valuation can be represented by an absolutely continuous measure if you speak mathematically. And informally, so this measure gives to every part some positive number. So indeed it is additive. If two pieces do not intersect, then the valuation of their union is just the sum of valuations. And continuity, so you could cut any piece in half or in any other proportion. So there are no atoms you can cut in any proportion. Okay, so then division is just a representation. So this whole disk, the segment is represented as a union of non-intersecting parts. Okay, and so the question, what is fairness? So there are two classical notions. So one notion is called proportionality. So if there are n agents, then each one thinks that his or her part is at least 1 over n fraction of the whole cake. So it is written this. So for any for an agent, his valuation of his piece is at least 1 over n of the whole valuation. So this is the classical notion. And alternatively, we can say that everyone thinks that he is at least as on average. And there are many procedures, many algorithms to find such a distribution. So they are polynomial. Okay, I think I skip what is an algorithm because I will not speak in details. Okay, so the other very important notion is envy-freeness. Envy-freeness means that everyone thinks that his or her piece is better than all other pieces. So formally, each agent I thinks that his share is not worse than any other share of any other agent. And it was a great open problem to find a procedure that searches for such a distribution, because envy-freeness implies proportionality, but not vice versa. Proportional cannot be envy-free. Okay, so there is always some envy-free division. Moreover, it's in two connected segments, and only 5 or 6 years ago, some concrete procedure, concrete algorithm was invented. Okay, so this is a brief history of these envy-free algorithms. So this is these are numbers for small n's, and here I want to mention an improvement by my student Georgy Sokolov. So he reduced number of cuts to obtain the envy-free division for 4 agents, and then for so for arbitrary n, so there were some procedures, so-called finite unbounded. So this means that there is no upper bound of number of operations. Yeah, so eventually they finish, but there is no upper bound. The breakthrough was in 2016 by Aziz and Mackenzie, but the number of queries was very, very high as 6-story exponent tower. And then they claimed that it could be reduced to 3-story tower. And another achievement by Georgy was that, in fact, it is just 2-story tower. In fact, the time could be made exponent. So the paper is under preparation. Okay, so this is the general picture about fair division. And now what's about it on a graph? So where does the graph live here? So the answer is the following. So in fact, the agents who are sharing this cake or something else, they could form a social network. And they could be aware only of their own wealth or their own pieces and about the shares of their neighbors. Yes, so they know what do they own, they know what do their neighbors own, but they have no idea what do some distant agent own. Okay, so here we can introduce the following notion, local envy-freeness. So local envy-freeness is just that every agent thinks that his or her share is not worse than any of his neighbors' shares. Okay, so it's he or she doesn't envy only to his immediate neighbors. Okay, and another notion called local proportionality means that the share of an agent, by his point of view, is not less than the average share of his neighbors. Okay, so here are connections between these criteria. So of course, global envy-freeness implies local envy-freeness. Yes, because if one does not envy anybody, then he or she does not envy to anybody among his or her neighbors. And also envy-freeness implies proportionality both globally and locally. But global proportionality and local proportionality are not connected to each other, and so here are two simple examples. So here we have four agents that form a circle, and this southwest agent. These numbers are shares from these agent points of view. So globally, there are four agents, and he gets 1/4 of the cake. But locally, his two neighbors get more. So he is unsatisfied. And another symmetric example. So here, the share of this agent is less than 1/4 of the total cake. But it is the same as the shares of his neighbors. So he doesn't envy to his neighbors, and so he is on average. So he thinks that his share is as large as average among his neighbors. Okay, and from point of view of these other agents, things could be completely different. So probably from point of view of this guy, everything is also fair. Okay, so what are the questions? So the questions is probably try to find more efficient procedures, more efficient algorithms for finding local envy-free partition and probably local proportional. So there is a recent paper by Chinese people when they propose just a single exponent algorithm for any graph. But probably for some particular types of graphs, it could be more efficient. And here we have some results, some theorems. So for trees and for bipartite graphs, we have also exponential algorithm, but with a lower base than in the previous paper. And also we have some other algorithms for some particular types of graphs. Okay, so it is about fair division on a graph. Now I have a remark. So this fair division could be also on hypergraph. Because the society consists of some small groups, and also probably it is important to have envy-freeness inside this small group. So we can, in fact, envy-freeness is always the same, but proportionality could be different. And we could compare proportionality in the hypergraph when inside the edge everyone thinks that he is not worse than the average of other agents in this group. And also we could consider the projection where just nodes are connected if they are in the same hyperedge, and talk about proportionality inside this network. Okay, so I think I show these another two examples. So here we have two triangles, two hyperedges. So here we have local proportionality, yes. So because this edge is connected to all three people. And he gets 1/4 of the total cake. But inside both hyperedges, he gets less than on average. Yes, so on average here we have 0.3 and he gets 0.25. Yes, and another example is here. So here we have no local proportionality because it is less than 1/4 of the total. But inside every hyperedge, this is greater than the average of these. Okay, so here we have no implications in either direction. Okay, so again we have a question of how to find a hypergraph proportional division. Okay, so and finally a few words about fair division of a graph. I think I can show here pictures. So the question is about dividing into connected components or into connected parts. So this is a historical illustration from 18th century. So this is so this woman is catching the Great, the Russian empress, and so this depicts the division of Poland between Russian Empire, Prussia, and Austrian Empire. So I show here. So there is a theorem that on a disk it could be divided such that so if a disk is surrounded by some existing territory, then it could be divided without envy, such that these parts are connected and border the existing parts. So, and this was precisely the situation with Poland, but this was not another historical illustration. This was not the story after World War II, because so there were 4 zones in Germany, and both zones included some part of land and some part of Berlin. So, and this implied some Berlin crisis, Berlin Wall, and everything here. And also I want to show a very beautiful example when the parcels are highly unconnected. So this is a town that is divided between Belgium and the Netherlands. So and probably so this line is the border between Belgium and Netherlands. So here it is shown better. Yes, so the yellow part is the Netherlands and the orange part is Belgium. So it's highly unconnected component. Okay, so here the question is if this space of goods is represented by a graph, so how to divide it fairly into connected parts. Okay, so I skip the concrete results. Okay, so let me conclude. So I think that the area of fair division is very important, and these networks that are underlying are also important. So this is why the research should be continued. And here, all graphs here are very simple, and probably in some more general graphs, probably for some more general classes of graphs, we should design new algorithms that would help to split something. Okay, so this is a small list of papers that this talk and our work is based upon. So thank you very much. So we have few minutes for questions.
Yes, thank you a lot, Daniil, for your really brilliant presentation. There is time for a short question. Is there any question from the audience?
Yes, by Ivan.
So please, Ivan.
My first question is about local proportionality. When you show the example, yes, we have local proportionality only in the red vertex, but in
yes, but
not in all vertices in graph. When we say about local proportionality, we say for any vertices on graph or for every vertices.
Yes, it should be satisfied for all vertices, but so here I show only the numbers from the point of view of this agent.
Okay, but when local proportionality works, but global not works.
Yes, so here
here
vice
global,
versa.
Here global works, but yes.
Yes,
here.
and here local works, and
but
global.
The vertex that upper than
yes,
red?
but for this agent, the numbers are also different.
Okay.
Because so these numbers are subjective, so they are from the point of view of this agent, and
okay.
the other agent could have completely different valuations.
Okay, understand. Thank you.
Okay, so are there any other question, very short, from the audience? If not, I would like to thank you very much, Daniil, again. Daniil,
yes?
How many people are there in presence?
7.
7. Plus 27 is 34. So we have a rather large audience. So thank you again, Daniil, for your beautiful presentation. And we move to the next speaker.